we are going to talk about the properties of pure substances. So in this video, I'm going to talk about pure substances first, define them, what they are. Then I'm going to talk through the phase change of pure substances, different phases, solid, liquid, gas, and how they change to each other. Then I'm going to show these phase changes on different property diagrams such as TV, PV, and PT. Then I'm going to show you how to use the property tables and talk about the reference states. And then to wrap the video up, we are going to talk about the equations of state with an emphasis on ideal gas equation. Okay, what is a pure substance? A substance that has a fixed chemical composition throughout is called a pure substance. Now, with this definition, many of the substances that we deal with, such as nitrogen, oxygen, carbon monoxide, carbon dioxide, and water, are considered pure substances. But a pure substance is not always a single element or a single chemical component, like the examples here. It can be a mixture. So a mixture can still be a pure substance if it has a fixed chemical composition. An example for that is air. Now, air is a mixture of different components, such as nitrogen, oxygen, CO2, and even water vapor. However, not all mixtures are pure substances. Consider a mixture of oil and water. Now, we know that oil and water, they don't mix that well. So consider a tank like this, and we have water and oil in it. So by experience, we know that water stays on the bottom and oil stays on top. Now, if I take a sample like this and check the chemical composition, I get 100% oil. If I do the sampling here, I get 100% water. And if I do something in the middle like this, I'll get 50% oil and 50% water. Now, as you can see, the chemical composition at these three different locations inside this mixture are different. So it is not a pure substance. Now, a mix of different phases of a pure substance can still be a pure substance. An example of this is water and water steam or water vapor. Now, consider a container like this. We have liquid water here, and then we have vapor or gas form of water on top. Now, again, if we do 3 different samplings and check the chemical composition here, in the gas form, the chemical composition is H2O. In the interface, it is H2O. And in the liquid, it is H2O again. So as you can see, a uniform fixed chemical composition throughout the tank. So it is a pure substance, although they have different phases. The same, however, cannot be said about air, for example. Now, we know that nitrogen has a condensation point or a boiling point at minus 196 degrees Celsius. Oxygen, on the other hand, boils at minus 182 degrees Celsius, right? So let's consider a tank like this where we are keeping some liquid air. So we have gas air here and liquid air here. And the temperature of this setup is minus 190 degrees Celsius. So if I take a sample from here, the liquid is very rich in oxygen, right? Because of the temperature. Now, if I take a sample from the gaseous form, it will be very rich in nitrogen. Now, as you can see, the chemical composition is not uniform or homogeneous between the gas and liquid phases, and so this is not a pure substance. By experience, we know different phases of pure substances. We know we have the solid, then we have the liquid, and then we have the gaseous form. The molecules of a pure substance in solid form are seated in fixed positions with respect to other molecules around them in some sort of a structured grid or lattice pattern. They cannot move out of their fixed positions, but they still can vibrate and oscillate in their seats. The bonding forces keeping them in this grid are rather strong. Now, if we introduce enough energy in the form of heat to a solid, the motion of the molecules increases, the momentum of the molecules increases as their temperature rises, their internal energy rises, and gradually they overcome the bonding forces that are keeping them as a structural grid. They go into the liquid form. Now, in the liquid form, there is no structural grid, but the molecules are still bonded together. Because of all of the energy that we introduce to the solid to make it into the liquid, a liquid state generally has higher energy than solid. Now again, if we introduce enough energy in the form of heat usually to the liquid, the molecules finally break free from that remaining bonding force, and they go truly free. They can move in any direction that they want, with any velocity that they want. There is no structure in space. And again, because of all the energy that we introduce to the liquid to break the bonds, the gas form has the highest energy level between the three states. Okay, so let's do a simple test. Let's consider a simple piston and cylinder system. The piston has no mass, and the pressure outside is 1 atmosphere, and we have water inside at 20 degrees Celsius. So this water is at room temperature, and we know that at 1 atmospheric pressure, water boils at 100 degrees. So water at 20 degrees is not about to boil. Now, a liquid that is not about to boil or vaporize is called a subcooled or compressed liquid. Okay, we are going to add heat to our system. Now, because of the heat, the temperature starts to rise. Let's say it goes to 40, and the water expands, right? Because of the addition of heat, the water expands, and the specific volume or the volume of our system expands as well. And the piston is now here. But the pressure is still 1 atmosphere, and everything is still in liquid water form. We can continue to introduce heat until the water inside has expanded all the way it can, and the temperature has reached 100 degrees Celsius. We are still dealing with water in liquid form here. Now, here, if we introduce 1 bit more of energy in the form of heat, a single molecule or a single drop will break free from the liquid and go into the gas form. So this liquid here at 100 degrees Celsius is about to vaporize. Now, a liquid that is about to vaporize is called saturated liquid. Okay, so we can continue to heat our system while the pressure is still 1 atmosphere and the temperature is still 100 degrees, but now a portion of our system is in liquid form while the rest is in gas or vapor form. Now here we are dealing with a mixture of liquid phase and vapor phase, right? And they are, now this state here where both liquid and vapor phases of water are inside the system is called a saturated liquid vapor mixture. Okay, we can continue this and heat the system up to a point where every last droplet of water has evaporated. So we have only vapor or gas form at 100 degrees Celsius. Okay, now in this situation, if we take one bit of energy or heat out of this setup, a single droplet or a single molecule of water will condense back into liquid form. So this vapor is ready to condense. Now, a vapor that is ready to condense is called a saturated vapor. Now, we can again continue to heat up the vapor, and while the pressure is still 1 atmosphere, go reach a temperature of, let's say, 150 degrees Celsius. Now here, again, everything is in vapor form or gas form. We don't have any liquid. But the interesting thing about the state of our pure substance now is that this vapor, this gas, is not about to condense. Now, a vapor that is not about to condense is called a superheated vapor. Now, based on this experiment and our previous knowledge, we know that at pressure of 1 atmosphere, the water starts to boil at T equal to 100 degrees Celsius, right? So for the pressure of 1 atmosphere, T equal to 100 degrees is called the saturation temperature. And vice versa, for the temperature of 100 degrees Celsius, the pressure of 1 atmosphere is called the saturation pressure. So if you want to have a more official definition, at any given pressure, the temperature that a pure substance starts to boil or vaporize is called saturation temperature. And likewise, at any given temperature, the pressure that a pure substance starts to vaporize is called the saturation pressure. Okay, so if we want to draw the results of our experiment on a diagram, let's say on a temperature volume diagram or specific volume diagram, we get something like this. So we started our test with water at 20 degrees Celsius. And then we started to add heat. So the water started to expand, right? The specific volume, the initial specific volume started to expand because we were introducing heat. Then we reached the temperature of 100 degrees, where the phase change started. During the phase change, the temperature remained constant, right? Until we reached the saturated vapor. From then on, the temperature rised again in the superheated region. So this area is called the compressed liquid. So let's go back to our previous test. The figure that we got area is called the superheated vapor. The area in the middle, this straight line, is the saturation mixture or saturated mixture. This point here is the saturated liquid. And this point here is the saturated vapor. Now, we touched on this topic briefly before, but the amount of energy that is needed, that is absorbed or released during a phase change, is called the latent heat. So when you take your system to 100 degrees Celsius at 1 atmospheric pressure, the phase change has not started yet. You keep adding heat to your system while the temperature remains 100 degrees, and the system goes from pure liquid all the way to pure vapor. Again, the temperature is not changing, but the phase is, and it requires a lot of heat. all that heat goes into phase change, and therefore it's called the latent heat or the hidden heat. Now, latent heat in general is a function of pressure and temperature of your system. So, for example, for water at 1 atmosphere, the latent heat of fusion, which is the melting or freezing process, is 333.7 kilojoules per kilogram, while the latent heat of vaporization, which is boiling or condensing, is 2,256.5 kilojoules per kilogram. Now, one thing that you need to pay attention to is that the saturation temperature is actually dependent or is a function of the saturation pressure. What I mean by that is they follow a trend, at least for water, they follow a trend like this, where this is a saturation pressure and this is the saturation temperature. Now here, let's say this is 100 degrees Celsius, so the pressure is 1 atmosphere or 100 kilopascals, right? But at a pressure at, let's say, 400 kilopascals, the saturation temperature is about 143 degrees Celsius. So as you can see, they are dependent on each other. What this means is that if we can increase the pressure, we can increase the temperature at which the phase change happens. An example of this is what happens in a pressure cooker. Now, inside a pressure cooker, the pressure is higher than atmospheric pressure. And so the saturation temperature is also higher, right? So the food is being cooked in an environment that the temperature is more than 100 degrees while the water is boiling inside, right? Whereas in a normal pot, because the pressure is 1 atmosphere, the maximum temperature that the water can get is 100 degrees. So a beef stew may take 2 hours in a normal pot, but take only 20 minutes in a pressure cooker. That's how it works. It increases the pressure so it can increase the saturation temperature of the water, so it can increase the boiling temperature of the water, and so the temperature that the cooking happens at. Okay, let's talk about property diagrams. Let's go back to our first experiment. We drew the temperature specific volume, and we started at 20 degrees. For 1 atmosphere pressure, we had a curve like this. Now, if we increase the pressure, let's say we increase it to 1 megapascal, what happens is that because of the additional pressure, our liquid at any given temperature has smaller specific volume because it's been under more pressure, it's been a bit more compressed, so it has less specific volume. So at 20 degrees, we start at a smaller specific volume. And now because the saturation temperature is a function of pressure, we reach the saturation liquid state at a higher temperature. And then the phase change happens, and then we go into the superheated region. Now we can continue this with higher pressures, and every time we get a bit higher where the phase change starts. Something that you need to pay attention to is that this line, which represents the phase change phenomena, so here everything is liquid, here everything is vapor. So this line, we call it the saturation line, shows the phase change process. Now, as you increase the pressure, as the pressure goes higher, this line gets smaller and smaller. The saturation line gets smaller until we reach a pressure where the line reduces to just a single point. Now, at this point, saturated liquid and saturated vapor are the same. There is no phase change process. This point is called the critical point. For water, The properties at critical point are listed here. The critical pressure of water is 22.06 megapascals, while the critical temperature is 373.95 Celsius. The corresponding specific volume is also called critical specific volume. And for water, it is 0.003106. We can have processes with pressures higher than the critical pressure, and you can still get them on this diagram. But for these processes, so these have pressures larger than critical pressure, for these processes, there is no phase change, there is no obvious phase change happening. So we have liquid up until a point, and then we have vapor from then on. But that exact point where the liquid turns into vapor cannot be pinpointed, cannot be known. It just happens. But as a rule of thumb, anything that falls on the left-hand side of the critical point, we treat it as compressed liquid. And anything that falls on the right-hand side of critical point, we treat it as superheated vapor. Now, if we connect all the saturated liquid points and then connect them to all the saturated vapor points, we get a dome like this. Now, let's clear this up in another page and we can continue talking. So this is still our temperature versus specific volume diagram. And this is our dome. So up here is the critical point. These are pressure constant lines. So this side of the dome is called compressed liquid side. Anything on the dome is saturated liquid. The area in between is a saturated mixture. Anything on this side of the dome is saturated vapor. And of course, anything right-hand side of the dome in this area is superheated region. Now this is called a TV diagram. We can draw the data on another pair of axes. We can put pressure and a specific volume here, and then get more or less the same dome. Now, in this diagram, the constant temperature lines are like this. Again, this side is compressed liquid. This is the critical point. This side is superheated region. This area is saturated mixture. Any point on this side of the dome line is saturated vapor. And anything on this line is saturated liquid. This is a PV property diagram. Now these diagrams, the PV and the TV diagram that we discussed so far, are really focusing, in this form, are really focusing on the phase change and phase equilibrium between the liquid and the gas. We can also add solid to these diagrams because there is a phase change between solids and liquids and solids and vapors as well, but I'm not going to do that because I want to keep this simple. We can talk about the phase change of solids with liquids and gases in another diagram, in a PT diagram. So let's take a look at a PT diagram. So this line here is the vaporization, and it ends on the critical point where we saw in the PV and TV diagrams. So this is the critical point. So if that is true, then this area down here is vapor, and the area here is liquid. This line here is the melting line. So this side over here is solid. Now, vapor and liquid, they have a vaporization line. Liquid and solid have a melting line, and solid and vapor have a sublimation line. Now I'm going to add another line here. This is also melting. Now the difference between these two melting lines is that this one is for normal substances, or the ones that contract on freezing. This line over here is for substances that expand upon freezing, like water. Okay, so let's take a look at this. So it shows that at different pressures and temperatures, we can have different forms of a substance. On a vaporization line, on a right pressure and a right temperature combination, we can have a mixture of both liquid and vapor forms, right? With the right combination of temperature and pressure, we can have both phases of solid and liquid at the same time. And again, with the right combination of pressure and temperature, we can have both phases of solid and vapor at the same time. There is this point in the middle, however, that at certain pressure and temperature combinations, we can have all three phases. Now, this point is called the triple point of a pure substance. Now, for water, triple point is achieved at 0.6117 kilopascals and temperature of 0.01 degrees Celsius. Now, what I mean by having all three phases, let me give you an example. Now, in a system where the temperature is 100 degrees, we can have a situation that half of the container is liquid while the other half is vapor. If we do not add any heat and we insulate the entire system, then the vapor and the liquid at 100 degrees Celsius will remain there. They will stay in a phase equilibrium. Okay? Now, if we add more heat, sure, the liquid goes into the vapor, and if we take heat out of the system, sure, the vapor condenses back to liquid, right? But if you put some ice inside of this as a third phase, if you put ice in, that ice cannot stay. It will melt down and condense some of the vapor back into the liquid, right? Because ice absorbs the energy and melts down at 100 degrees Celsius. So the pressure here was 1 atmosphere. Now consider the same situation. This time the pressure is 0.6117 kilopascals. And the temperature is 0.01 degrees Celsius. Then I can have a layer of ice topped with a layer of liquid water and topped with vapor. Again, let's say everything is insulated and no heat is coming in or out of the system. If that is true, then this ice, this liquid, and this vapor can all coexist in the same system at the same time, or in other words, they will be in a phase equilibrium together. So that is the triple point for you. Triple point is a situation where all three phases of a pure substance can be together in a phase equilibrium. Okay, now we are ready to talk about property tables and reference states. For most substances, the relations among thermodynamic properties are too complex to be expressed by a single equation. So therefore, these properties are usually given in table forms. Now, here's an example. Now, this is a property table. As you can see, various properties of water is given based on the saturation temperature or based on the temperature, right? So this column here is the temperature, this column is the saturation pressure, and these columns are showing the internal energy. These are showing enthalpy, and these are showing entropy. So enthalpy is internal energy plus pressure times a specific volume. We show it with H, and this is the equation for it. Now, we'll talk about enthalpy in future videos, but enthalpy usually shows up when dealing with control volumes and the situations where a fluid is flowing in and out of a system. But for now, just take the definition of enthalpy as the summation of internal energy and pressure times a specific volume. Now this equation, this form, has a unit of kilojoules per kilogram. We can have the extensive one, as in capital letter H is capital letter U plus P volume, and the unit will be kilojoules. Okay, with the definition of enthalpy out of the way, let's focus on the table. As you can see, there are two specific volumes listed for each temperature. One of them has a subscript of F, the other one has a subscript of G. And for the internal energy and enthalpy and the rest, there is a third subscript, which is Fg. What are they? Now, property Y of F represents the property Y of the saturated liquid. Y of G is the property Y of saturated vapor. Y of Fg represents the difference between Y of G and Y of F. So for example, at the temperature 25 degrees, Y of F shows the specific volume of the saturated liquid, and V of G represents the specific volume of the saturated vapor. Let's show that on our TV diagram. So if this is TV, by the way, TV, TH, TU, TS, all of these look the same. You have the same dome, and we have our constant pressure line. So this here is V of F, or H of F, or U of F, or S of F, whatever. This one here is V of G, H of G, U of G, or S of G. This distance is VFG, or H of FG, or U of FG. And this is your saturation temperature. Now we have values for this point and this point. But what happens in the middle? Let's talk about that. Now in a saturated mixture, we need to introduce a new property so that we can pinpoint the exact values of specific volume, enthalpy, internal energy, and everything else. We call this new property the quality of the mixture. We show it with X, and we define it as the mass of the vapor divided by the total mass. So the total mass is mass of vapor, we show it with m of g, plus the mass of fluid, we show it with m of f. Okay, how does this help us? So let's consider an example. So the volume of a system is the volume of the gas plus the volume of the fluid when fluid and gas are in a saturated mixture situation. We also know that mass times a specific volume is equal to volume. So total mass times the specific volume of our mixture is the mass of the vapor times the specific volume of the vapor plus the mass of fluid times the specific volume of the fluid. I'm going to divide both sides by the total mass and get the specific volume is mass of gas over total mass plus mass of fluid over total mass times a specific volume of the saturated liquid. Now do a bit of algebra and we get x v of g plus 1 minus x v of f. We can rewrite it into this equation. So just to recap, in a saturated mixture, any property can be found using these equations. So what does this x show? So if this is our TV diagram and this is our constant pressure line, the x shows where on this line we are. This shows x. Now, one thing to keep in mind is that because x is the mass of vapor over the total mass, it has a range of 0 and 1. 0 is when the system is in saturated liquid form, and 1 is when the system is in saturated vapor form. Another thing to consider is that the y that you get from these equations must always fall between the value of y of f and y of g. So this is your checkpoint. If you use this equation, find a y which is not in this range, you've done your calculations wrong. Something's wrong. Okay, but how to use these tables? How to find the state of our system? Now, it's kind of easy. You just need to remember the state postulate. So the state postulate says we need two intensive and independent properties, right, to pinpoint the state of our system. Now, intensive independent properties are the ones that we usually encounter in thermodynamics are the specific volume, internal energy, enthalpy, entropy. We don't know entropy yet. We're gonna talk about it later in later videos. Temperature and pressure and quality for the saturation mixtures. But even if we have two independent and intensive properties, how can we use them with a table? So let's get to it. Let's say you are given the temperature and the specific volume of a system. So you have these two properties. What you can do is you can go check the property tables. So let's say the temperature is given, the temperature is 75 degrees Celsius, and the specific volume of our system is 3.2 meters cubed per kilogram, right? So these are the two independent intensive properties that we have, and now we want to find the rest of the properties of our system, or in other words, we want to pinpoint the state of our system. So we are going to check the tables. Let's do that. Okay, so this is a property table, right? I'm going to check the temperature here. So the temperature column is here, and 75 degrees is here on the table, right? That is 75. Under the columns of a specific volume of saturated liquid and saturated vapor, you can read two numbers. This is the saturated liquid, and this is the number for saturated vapor. So at temperature of 75 degrees Celsius, specific volume of saturated liquid is 0.001026, and the specific volume of saturated vapor is 4.1291, both meters cubed per kilogram. Okay, the volume that we have is larger than V of F, specific volume of saturated liquid, and is smaller than V of G, or specific volume of saturated vapor. What does it tell you? Let's take a look at the diagrams that we had. So if this is our TV diagram, this is our dome, and this is the pressure that we're dealing with. This is V of F, this is V of G. The volume that we have is somewhere in between here. So we are in this area. So we are in saturated mixture area, right? Now that we know we are in the saturated mix area, we can find the quality. Always find the quality when you are in the saturated mix area. So a specific volume, remember, is 1 minus x V of F plus x V of G. Now in this example here, V of F is known, is 001026. V of G is also known, 4.1291. Actual specific volume is also known, 3.2. The only unknown is the quality. If we do a bit of algebra, we find x is 0.7749. So we found the quality of our mixture. It means we are 77% vapor, 23% liquid in this mixture. Now, if we want to find any other property, let's say we want to find internal energy, all we need to do is say, hey, the internal energy of the mixture is 1 minus x, we already know, U of F plus x U of G. Plug in U of F from the table, U of G from the table, and we can find U. We can find H, we can find S, we can find all the other properties. One other thing that we can conclude from knowing that we have a saturation mixture is that pressure is the saturation pressure at T equals 75. Now, because we have a phase change, pressure is a function of temperature. So all we need to do is go check the table for temperature of 75 degrees and read the saturation pressure. There, by knowing only two intensive independent properties, we found all the other properties of our system. Now, what happens if, in that example, the specific volume that we had was smaller than the specific volume of the saturated liquid at 75 degrees. Then let's take a look at our diagram. So this is again T, and this is the volume. This is our dome. This is our V of F. This is our V of G. So we are somewhere like here. Now this area is compressed liquid. Right? So if the volumes are smaller than the specific volume of saturated liquid, we can conclude that we are in the compressed liquid area and go check the table for compressed liquid. If our volume was larger than the specific volume of saturated vapor, we would end up somewhere like here, which is the superheated region, right? So we would conclude that if V is larger than V of G, we are in the superheated region. And we would go check the table for superheated properties. Now, please take note that the volume can be replaced by U or enthalpy or even entropy. The conclusion is the same. Now, usually there are tables for both saturated mixture and superheated regions. There are also tables for compressed liquid, but not as much. So usually no tables for compressed liquids. So what we can do is that we are going to approximate. How? We are going to say the property that we are looking for a compressed liquid is approximately equal to the property of saturated liquid at the same temperature, right? So because we don't have a table dedicated to compressed liquids most of the time, sometimes you have, but most of the times if you don't, what we do is we read the temperature, we decide that, hey, if we are in the compressed liquid, but we don't have enough data, we go and read the property at the same temperature for saturated liquid and take it as the property of our compressed liquid. So keep this in mind. For saturated mixture and superheated region, there is no need to worry. We always have tables for them. Now let's talk about the reference points or reference states. As we discussed, many of these properties, especially the internal energy, enthalpy, and entropy, cannot be measured directly. On the other hand, we are only interested in the change of the values of these properties. We have relations and equations that show the change in these properties. Okay, so what we can do is we can assign a certain state as the reference point and put the values of some of these properties 0 at that state, and then use those equations and relations to build up a value for these properties at different states. Let me give you an example. Back to the table that we had for water at a temperature of 0.01 degrees Celsius and a pressure of 0.6117, in other words, the triple point, we are assuming the internal energy to be 0 and the enthalpy to be very close to 0. The enthalpy cannot be 0 because remember, enthalpy is internal energy plus P specific volume. Now, specific volume is a physical property that can be measured directly. And as such, it has a number here, right? Internal energy, on the other hand, we cannot really find the value directly. So we are going to assign it 0 for water at this situation. And enthalpy, because of this equation, follows to be 0.001. And then we build the rest of the table based on this 0 value of internal energy. So this is our reference state for water. Now, this is how we work. For different pure substances, we take different reference states. We assign 0 values to some of the properties and then calculate other properties based on the equations and relations that we have. In many situations, we really want to be able to relate different properties of a system together using a single or simple equation. That will be always easier than using tables, right? Now, unfortunately, that is not really possible for most of the cases, but when we are dealing with gases, pure substances in gas forms, especially when we are dealing with gases in low density, meaning high temperatures and low pressures, there are certain equations that can relate different properties of the gas together and give us accurate results. One of these equations is called the ideal gas, which is the most famous form of equations of state, and it says pressure of the gas times its specific volume is equal to gas constant times the temperature of the gas. Now, you need to pay attention that this temperature is the absolute temperature. Now, absolute temperature in thermo means temperature in Kelvin. Now, just to refresh your minds, Kelvin temperature or Kelvin scale is the centigrade plus 273. So water boils in 100 degrees Celsius, which is 373 Kelvin. Okay, this is the conversion rate that you need to use. So here, make sure that you are using Kelvin. So R is the gas constant. Now, how do we find it? R for each gas is the universal gas constant divided by the molar mass of the gas. Now, what are these? The universal gas constant is 8.31447 kilojoules per kilomole Kelvin, whereas the molar mass is different for different gases. Molar mass is the mass of 1 kilomole of gas. For example, 1 kilomole of nitrogen is 28 kilograms. The values for the gas constants are usually given in tables, so don't really worry about the molar mass and the universal gas constant and things like that. Usually the R or the gas constants are given. Now, if we manipulate the ideal gas equation and say, hey, PV is RT, and then say, okay, R is the constant, so PV over T is a constant, right? So from this equation, writing it for two different states of the same gas with the same mass, we can conclude that P1 V1 over T1 is equal to P2 V2 over T2. Now, this is a very important conclusion. Now, for the same gas in the same system, we can always use this equation to relate the different properties of the gas at state 1 to state 2. We can write this equation in other forms as well. We can rewrite it in the form of P1 times the actual volume 1. This one was the specific volume, whereas this one is the volume. Now, as I said, ideal gas equation is giving us very good results when dealing with low density gases, meaning usually high temperatures and low pressures. So in these situations, the ideal gas equation is very good and very accurate. Now, for our applications in thermodynamic course, we can nearly always use the ideal gas equation for air. Okay, so whenever we're dealing with air, with oxygen, with nitrogen, with carbon monoxide, carbon dioxide, we can always use the ideal gas in thermodynamics. On the other hand, we cannot use it when dealing with substances that usually undergo phase changes, like steam or water vapor. Never use it with steam, never use it with refrigerants. Like, we are going to talk about refrigerants and refrigeration cycles and such later, but a refrigerant basically goes through different phase changes in a cycle in your refrigerator. So it is a very good bet not to use the ideal gas equation when dealing with that as well. One of the most famous refrigerants is R134A. So for steam, water, refrigerant, things like that, never use the ideal gas. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like, as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again, and see you in another video.